Assignment 1 in this pile, right? So no one's going to add anything as I talk here. I think you would. Okay, so I asked you 3 questions in assignment 1. The first one was to calculate how much better your sensitivity would be for a proton NMR if you went from the 300 to the 500 megahertz instrument. The second one was to think about how much less sensitive a carbon NMR experiment is relative to a proton NMR experiment. And then the third one was to think about the sensitivity of a fluorine NMR experiment relative to a proton NMR experiment. You have all of this already. I gave you this formula for the splitting in energy and kind of rationalized it in a hand-waving kind of way. And we worked through in class how we can basically rearrange this to give this formula that relates the precession frequency to the field strength times the magnetogyric ratio divided by 2 pi. So I think that probably made sense, hopefully. So the first question was, what happens to the sensitivity when we go from 300 to 500 megahertz? Sensitivity is a bit of a slippery concept, as we'll see. So for the time being, let's just focus on the size of the magnetization vector m. Okay. We worked through, for a 300 megahertz experiment, how the difference in population of the upper state versus the lower state was very, very small. A difference of about 4.85 per 100,000. We did that in class. If you take all the numbers for you take that energy splitting that we derived for the 500 megahertz experiment, plug that into the same formula, you find that the difference in population of the upper state versus the lower state is now 8.08 per 100,000. So in other words, we increased the field strength by 1.67 times. Therefore, that led to an increase in the magnetization vector by 1.67 times. That's an important take-home message, that the population difference that we're getting here is directly proportional to the splitting in energy, which in turn is proportional to the applied magnetic field. So does that mean that the sensitivity has improved in going from a 300 to a 500 of 1.67 times? Well, it's more complicated than that. We'll get to that in just a minute. But that would be a reasonable answer to come up with. Question 2, what happens when we go from a proton experiment to a carbon experiment? So again, we've got all the energies. We basically worked through them in the previous class. Okay, we've made a decrease in the magnetization vector by a factor of 4. Again, that turns out to be linearly proportional to the size of the magnetization vector, so that's decreased by a factor of 4. So we might say, maybe you're thinking that a carbon experiment is about 25% as sensitive as a proton experiment, and then of course there's not as many C13s, so 1.1% gets you to a total value of 0.275%. Is that necessarily sensitivity? Slipperier than that. We'll get to that in a minute. And then the third question was, what happens in a fluorine NMR, changing from a proton to a fluorine NMR? I gave you the magnetogyric ratio for 19F, and it turns out that that's about 94% the size of the magnetogyric ratio for a proton. And so we might say that the sensitivity for a fluorine NMR, we might say, well, maybe it's 94% as sensitive as a proton. But then, if you dig a little bit deeper, and particularly if you look in your book, okay, you'll find this table of sensitivity values and natural abundance values. And you'll see that the sensitivity in a fluorine NMR experiment is not 94% as sensitive as a proton experiment. It's actually about 83% as sensitive as a proton experiment. And you'll see that the carbon experiment is not 25% as sensitive as a proton experiment. In fact, it's quite a bit worse than that. Okay, so this is before taking into account the natural abundance. So it's actually very low. So what's going on? Well, it turns out that if you kind of think about what you're doing in an NMR experiment, right? You're inducing this magnetization vector, and then you're measuring the effect of that magnetization vector as it decays back to its ground state. And so the actual NMR experiment is going to depend on three things. It's going to depend on the size of the magnetization vector, right? And that's going to be proportional, as we've already said, to the magnetogyric ratio times B naught, the applied magnetic field. Okay. Divided by temperature. Okay. It's also going to depend on the ability of the receiver coil to detect the precessing magnet, which again is going to depend on the strength of the nuclear magnet. In other words, that's also going to be proportional to the magnetogyric ratio. And then it's also going to depend on the frequency at which the magnetization vector is precessing. And that's going to be proportional to the magnetogyric ratio times the applied magnetic field. And so if we put all of these three things together, the overall sensitivity in the experiment should be proportional to the magnetogyric ratio cubed times the applied magnetic field squared divided by temperature. So, for question 1, if we plug all these numbers together, going from a 500 megahertz to a 300 megahertz experiment, we need to square the values there in Tesla. That gets us to our 278% change in sensitivity. Likewise, for question number 2, we need to be cubing these magnetogyric ratios, not just taking the simple ratio of the magnetogyric ratios, it's the ratio of the magnetogyric ratio cubed. And that's how that 1.59% number comes from. And then that's multiplied by the natural abundance. And so the actual sensitivity here for a carbon experiment is really, really, really bad. Okay. But just good enough that we can acquire a carbon spectrum is useful. Okay. And then similarly for the fluorine experiment, it's the magnetogyric ratios. The ratio of the magnetogyric ratio is cubed, and that's how you get to that 83% number as opposed to 94%. Okay, does that make sense? So the key takeaway message here is that it's this formula that really determines your sensitivity. It's because all these three things have to be taken into account. Yeah?
Could you send this slide to us by email?
I would be happy to send that slide to you. I will forget as soon as I leave this room, so if you could send me an email, I will reply. Yeah. Good. Any other questions?
Yeah, with respect to that, I saw that the equation for the sensitivity was the magnetogyric ratio cubed multiplied by I multiplied by I plus 1. And I used that and it got me to the same answers.
Yeah.
What was I?
Oh, the spin.
The spin.
Spin.
Yeah.
Oh,
Yeah.
That's
So I'm thinking about what happens when you go away from a proton.
was more the bio-stuff, right? The paper said it was more biology based.
Yeah, I think it was, yeah.
Yeah, but it's because they're the ones that care about the nitrogen 15 experiments for the cross labeling in proteins. So where does the spin come in terms of sensitivity? I mean, it kind of makes sense intuitively that spin has to factor in here, but off the top of my head, I can't think why it would be I and then I plus 1. Do you have a ready answer to that?
No.
No.
Both carbon and spin plus 1/2.
Yeah. So it works out to the same answer, obviously, for a spin 1/2, but it won't work out to the same answer if the spin is not 1/2.
Oh, okay, I see.
And that's where I'm not sure. I'm not sure.
Okay.
Yeah, I'm sorry.
And I wonder what happens when the spin is minus 1/2. Because that's nitrogen, silicon.
Yeah, I'm not sure
That's
there
your
either.
absolute value.
I've never really thought of I've so seldom even run a.
Wasn't it the number of spin states you could have? You said
well,
it's
that's
the
the
number
Boltzmann.
of.
Mm-hmm. Yeah.
Yeah.
Yeah, this table here.